Okay, my friends, we're going to get deep into neutrinos versus photons. Like, once again, Fermilab, they're doing most of the research now, it appears, into these tiny little particles. I have a particle accelerator that works fabulously, and we can see these neutrinos, and we can see actually photons. So let's get into it. Okay, my friends, here's the problem with neutrinos and the way they do particle acceleration at CERN, Fermilab, and the rest. They're using huge particles that come in, crash, and cause all kinds of just debris, literally debris. There's almost nothing there that they can really understand other than to keep looking deeper and deeper and deeper to try to find the smallest particles. Well, we started with light, which is much smaller than protons. So we actually saw the particles, which are the neutrinos. Okay, let's just look this through real quick. Science focuses on these neutrinos, the vital clue to a theory of everything, because that's exactly what they are. 100% of everything is made of neutrinos. Listen to this. 90 years after its prediction, 25 years since the Nobel Prize was awarded for its discovery, the neutrino particle is still surprising us. It may, in fact, be the key to understanding everything. A neutrino is charge-separated particles. Here's the key point in this whole thing. According to the Standard Model, the high point of 300 years of physics describes the fundamental building blocks of matter and three non-gravitational forces that glue them together. The neutrino should be massless. We know that's not the case. Okay, so what are we looking at here? We're looking at particles coming in and smashing into each other, creating huge piles of debris, literally, with all these little squiggly little things going on. And all they really can do is look to see what they can find is the smallest particle that consistently shows up. And they found these neutrinos. And they are what make everything there is these two little tiny particles. I'll show you. So, neutrinos are one size fits all? No, there is a twist to this story, a major one. The electron neutrino is merely one of three types, they call them flavors, of neutrinos. The electron neutrino is associated with the electron, that's the glowy part, the one that really does some burning. But there is also the muon neutrino, which is just a mass, associated with the heavier muon particles. That's just a massive particle. And then a tau neutrino with even heavier tau particle. Well, let's see if we can find these. Okay, you will never see anything clearer than this. This makes everything obvious. There's a particle that comes through and goes forward called a photon, and that's what it looks like. Now, okay, I'm going to show you the particle that creates this wave. They say particle wave duality. Absolutely, because there's a particle back here that looks just like this, and it has a pushy, glowy magnetic field in front of it that pushes every other particle's magnetic particle away, so it creates a wake just like it does with a jet fighter or a boat or anything, and that's because it's pushing against those. They take on a little energy, and this takes on a lot of energy. It's push to shove back. As this goes forward, the leading glowy part charges up, and then it flips. And then this is the chargy part, and it charges up and flips again. That's what causes them to spin. Then they can come apart and become what's called an electron, which nobody ever knew about this dark part. Nobody ever knew that was there. All they knew was there was a glowy electron that did work and burned people and all that. This is really where all the weight is. All right, and it's a carrier. They know about that, and they've seen this now. It's called a muon. And they've seen the electron neutrino, and they see the muon neutrino. And then the tau neutrino, I think I have seen that as well. But don't forget, this is what causes the field in front to concuss, creating the wave field particle duality. Now this is where it gets real interesting, because the efficiency of a particle accelerator is shown by the luminosity that it creates when it accelerates a particle. And you don't get any more luminosity than that. Okay, CERN just put out a thing saying the way they can tell how good their particle accelerator is working is how much luminosity they get. I just did this a video on this the other day, right from CERN. It's exactly what they said. And now they're getting much more luminosity because they're focusing. That's what we did. This is focus. That's the reason this particle is so highly energized. These same particles are up here. You don't see them until they get pushed back against. And this is reverse EMF. That's the only reason you're seeing them. You see this field? You see that field? Look at it carefully. It's the exact same field as this. Exact same field as this. Exact same field as that. We didn't see these coming. They didn't just show up here for no reason. They were back here. They were coming right along with this one. But this one is dead nuts. Bang. Right straight through the center. These were not. These I could see, I believe I could see them as tau. We're going to go looking at this in a second, in how this manifested itself from just that wave that I showed you, and now all of a sudden it's accelerating due to the Venturi. Alright, this is pretty outrageous. This is the photon. Okay, that's that red photon of light, and it's split, and the black separated from the white. Alright. Now, this is the muon neutrino, the black ones, and these are the electron neutrinos, the white ones. And they perform, and they do exactly what CERN says. The black one is a fixed particle, it's heavy, it smashes things. The white one has virtually no mass to it, but it burns things like hell because of its field. So let's just go over this again. I just don't want you to have any misunderstanding here. This photon, you see it, has a field around it. And that was that field around it that was pushing all those other particles, so they were glowing all around the field, as you recall, I'm sure. Now, what happened? Why do we see this here? Because we never saw this before. The only reason we see in this is because it's just about to concuss at the Venturi. I'm going to show it. I'm going to expand this in a second. You're going to see. But before I do that, don't forget, this is what they would call a gluon, which is really an electron, but it consists of the two things, the electron neutrino and the muon neutrino. The two of them together make what we would always consider an electron. And that will burn you. It will create power and energy and light and all that stuff. Well, it creates light because it gets attached to it as a photon. Two of these together make a photon. That'll bounce off you. This will burn into you. And it's static, it's lightning, it's electricity. It wants to seek ground. And why? Because ground appears to be completely loaded with these dark particles. That's what the white wants to attach to, is the black. And we could separate them, and then instantly they will come back to the black. Now, don't forget, these are the particles. Electron is both the muon and electron neutrino. Photon is two electrons together. They would call that a gluon because the two of them are gluon together. And the photons, they understand that's a photon. All right, so let's come back to this again. The electron neutrino was the white one, and it's associated with the electron. It is the electron, really. There is also the muon neutrino, which is the black one, associated with the heavier. That's the heavy one, and that's true, it's the muon. Now, there's the tau neutrino with even heavier tau particle, which is heavier than just the muon. It's actually a photon with two heavy particles and one light particle. Alright, this is pretty outrageous, but it appears to be the case. I believe these are the tau muons. You see they have one white and two blacks? One white and two blacks. Then they stack up at the Venturi, and it looks like they start to take on energy, and you get two whites and two blacks. You see here? That's the same particle, and now it's turning into a little box of whites and blacks. Now, the forward leading white one charges up almost instantly, and it flips. So now it has the lower leading white one will charge up, and it'll flip again. But it doesn't have time because it hits the Venturi right here and explodes. So what do we see? We see the gluons. We see a photon altogether. We see two electron neutrinos, two muon neutrinos. Here we see them all turn into just free for all, white showers and the black ball. But back here, I believe, is the tau. It's heavier than this. Well, why would it be heavier? Because it's got two blacks and one white. This has two blacks and two whites. All right, it looks like it's a heavier particle to me. The black is where all the mass is. And I did some calculations on this, and I'm going to explain it to you because I have it right here. And we're going to look at it. 207 times heavier, they say. So we can, once we know that the muon is 270 times heavier than the electron neutrino, we can do some calculating. Alright, so here it is once again. I'm not showing the tau neutrino, I'm just showing the muon, sterile muon, the electron shower, because before they were attached together, now they've separated at the Venturi. And that's what they're looking for, is head-on collisions. We didn't need to do head-on. We made them come sideways into each other to get through that slit. There's a Venturi in here. You can't see it because there's so much energy it obscures it. But the Venturi is just about like this. And it's so small that the black ball can't get through. Only the white, because the white can squish down. And it goes right through there. This is just so energetic, we're seeing a big ball of whiteness. But there's actually a Venturi there. And that's what forces the fields to actually slam into each other this way. And then the black balls are like bowling balls. And they just slam that white and just keep slamming it through there until it squirts through. Then it reattaches here. The blacks don't care about being right on top of each other. They have no pushing to anything. They only want to attract the white. And they do instantaneously. It comes back. I mean, this is light, so this is the distance light travels before it reattaches. That's pretty stunning. You see this? This is MIT. They're showing light spinning. Well, it doesn't spin that way. It spins this way. A right-hand spin. All right, this is a left-hand spin. You know what this is going to do? This is going to pull its field into itself. And we had one that did that. It's the most unusual one we've had. Let me show you that. Okay, these are the Higgs fields coming at us. And the only reason we're seeing them is because these white sprits have concussed with the black particles, and now they're starting to take on a weight. Just to be sure I don't lose you, don't forget, this is the light particles, they're photons, and apparently they look like they were tau neutrinos at some point right in here as they just started to concuss. Then they turned into full neutrinos, then they slowed down because they're backing up against here. So here I think the speed of light's been increased. It sure looks like it to me. But I know the neutrinos, they say, don't quite go the speed of light, and I can understand that now because these are bouncing back and forth, so it's hitting like a pillow of fields. And the white is being able to squirt through these, but the blacks just keep pounding them. So here we had photons, and then as they started to stack up, they turned into electron neutrino, tau neutrinos, and then the electron neutrino with the muon neutrino attached to it, and then the sterile muon and the electron showers. Back to reassembling, back to being regular light particles, back to being like this over here. And this pattern is only created because the light is spinning. Some spins off this way, and some spins over this way. And when they do, they push the other guy away. As I've shown this many times, when you inject charged particles in outer space into a vacuum chamber, they set up lines of just exactly like this, exactly, because they're pushing each other away. They don't want to be next to each other. These are not flap. This is a single slit. All right? These are repulsion patterns. Had nothing to do with flapping waves and so forth. So I've shown you, hopefully it makes sense to me. Tau neutrinos are here, photons, tau neutrinos, then these other new styles of neutrinos, and then the stereo muons, electron showers, and back to being photons. Now don't forget, we just saw all this. I explained it, I hope, well enough that you understand. If you were standing right here before these reconfigured, what would you see? You see them reconfiguring out here and over here because they're able to jump right in on the edges, but not in the center. You're going to be right in the center looking into the Venturi, and the light is coming directly at us. We're going to be right here. Let's see what we would see. All right, check this out. We're looking directly into the Venturi, directly straight into the laser. You see these little tiny spritzes of white? And they're going to be coming all over this place. These are hitting these particles here, which are the black particles, turning them into Higgs fields. We haven't gotten far enough out yet to hit the Higgs fields. We're so close to that Venturi that we are still in the whiteness, if that makes sense to you. Remember I told you where we were standing? We were in the white, so we're still here. If we came back out here, we would be in amongst all these Higgs fields too, and I'm going to show you a shot of that as well. This is the one I want you to pay attention to. That's the reverse spinner. Remember I told you before MIT had it wrong? They were going left-hand spin. You have to go right-hand spin. A left-hand spin drags the field inside and creates a very, very crazy situation, which I will show you. All right, check this out. This is that white spray coming through and smashing into the rest of the universe and creating all these Higgs fields. Look at those Higgs fields, and I can show you these Higgs fields appear to be the union of the black back to the white, because here it's totally white, and somehow it pulls the black back into it, and we can actually see them reassembling. Look at how that powerful that is. Oh, you saw all those Higgs fields, and every one of them has a tip to it, and these are the tips, and the tip of it is where the black and the white rejoin. Back here, they're still not joined. They are in the depression behind the leading tip that's coming out at us, and this is where the fusion back to the black particle and the white particle occur, as far as I can tell. It's what it looks like to me, because that's when this occurs and this occurs here, and it's always at the tip you have the black attached to the white. Every now and then you'll catch one here and there that will have reassembled deeper inside the wave, and it must have hit something head on, or I don't know what caused the ones in here, but look at how elegant that pattern is. This is all very, very serious information. This is not just joking around. So I think it's time to look at this very carefully, because what we need to do is take into account the dipole nature of these particles, the dipole nature of them. I've shown a dipole coming out of your ears. That's what exists, is these muon and electron neutrinos make up what we call an electron. Two of them together make a photon. 1,836 of them or so make up a proton. 1835 actually. 1836 is a neutron because it has an even number. And then that's one, what they always consider a proton, and that's one stable state. You add another one, or two, and three, and four together, and they keep staying sort of stable at that period, at that number of electrons in a ball. All right, you have a few less, you have what they call an isotope, and it doesn't want to be there. It wants those few more, which is called a half-life. It'll start to attract something to get back to stable. Or if it has too many, it'll shed them to get back to stable. And that's radiation. All right, and those are unstable atoms. And if you look up isotopes, do some research. Look up isotopes. And you see each one of these things has like 20 or 30 different types of the same particle. Even hydrogen has hydrogen 1, 2, 3, and it's all over the place. Right? Hydrogen is almost completely electrons. After you get up in here, you start to get into some mass that doesn't explode like hydrogen. You ever see hydrogen explode with a little bit of oxygen in it? It'll blow your eardrums right out of your head. See, they're going back to starting to say, well, maybe we got things a little wrong here. Let's rethink the universe. Neutrino oscillations, which is what I showed you, these will go boom, 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 boom. And then when they start to fall apart, well, okay, they say it maybe it's time to start rethinking the early universe, because neutrino oscillations, which is the flip, 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 may reveal the existence of a fourth sterile neutrino. I showed you, it's a black ball, interacting with matter so rarely it makes the other three flavors appear positively sociable. The black one's dark matter, that's why they never see it. The total mass of all three types of neutrino has consequences for the universe because neutrinos are the second most common subatomic particle. The second most common, but let me tell you something. They make up the first most common, which is photons. The two of them together make up a photon. We know this now. In the early universe, their considerable gravity would have helped matter clump together to make the first galaxies, which is that black dark matter. And there may be more dark matter than there is white matter. I don't know. It says the more massive neutrinos are, the earlier they would have slowed down after the Big Bang. Well, because they are gravity, that's true. So they have to rethink everything just going and not trying to get pulled back to each other. The black pulls stuff back really hard. After a nuclear bomb blast, everything goes out and then it all starts to suck back in. Because the black particles do not want to be alone. Okay, if you haven't seen this before, I'm going to tell you right now, the core of every atom is the dark matter. Surrounding it, they push all the white particles out, so the black particles sit in the middle. That's why it's dark matter. We've never seen it. It's obscured by a complete surrounding of the white particles. When an atomic bomb goes off, the white Bernie particles compress and then they go outwards. What we're going to see is this house is going to burn and then it's going to explode, because what happens is when these concuss, then they go outward. The only thing that's going to hit this first is the white particles, and it's just going to be as white can be, and it's just going to burn. No movement whatsoever, no concussion at all. And then a second later, the black ones come, smash it to bits. And then a second later than that, you can see the stuff coming back to try to get back to what's left of the black particles back where the bomb originated from. Because all the black particles won't go, but all the white ones will go, every single one of them. And so it's going to be sitting back there with a bunch of blacks saying, come on back, and they come back. So here it goes. Keep your eye on what's going on. This is Teapot Apple II Q House Atomic Bomb Effects. Atom Central. Here we go. Boom, there he goes. Look at this. Look at it burn. And then goes that. You see? Let's go back here and do it a little bit slower so that you can really understand what's going on. Alright, so let's get back right to here. Everything's fine. Having a nice day. Oh, I have a cup of tea, please. Now, watch all of these things. They're just going to smoke. This is just going to smoke and burn. Because all it's getting hit by is the non-weight electrons. Here goes. Now, we're 25% of even slow motion. So, boom. I'm stopping it as we go along. That is just nothing but electrons. Saturating the air with electrons. Well, electron to electron creates, push to shove, creates heat. So this, the electrons bouncing back from this, these coming in will just smoke this up. Even though they don't push it anywhere, it's their fields. The fields concuss. You see it? The fields concuss. They push in against this, and they try to push back a little bit. The fields concuss. It's just barely rolling back. And that's because of, this does have a little tiny weight to it. I figured out it's like less than 5% of the weight of the electron, muon, neutrino attached together. So it's less than 5% is the weight. And that's why it burns and doesn't push. All right, let's keep going. See, it's now starting to wrap around. You can see it's pushing a little bit. There's a little bit of push. This stuff is pushing back from the thing, but not like we're going to see in a second here. Right? This is almost nothing. Because in now will come the black particles. All right, so here we go. Boom. Now, it's actually almost combusted everything that's burnable. Now, here comes the black ones. Okay, let me turn the sound off because they're just going like that. All right, here it goes. Now, here we come. I'm going to, boom. Now, I stopped it. What's going on now? Everything's going. This is what this is. Now whoops, I'm sorry. That's what that is. These are the black particles hitting. You see it? It's caved the whole front end. It's just boom. Get the hell out of my way. Everybody get out of the way. I'm coming through. See it? Look at that. It's just torn it to shreds. Now, watch the next important thing is all of that stuff that's going back will start to come back this way. Because the black particles want them back again. See it? Going out, 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 out. No burning. No more burning. See, watch it turn around, come back. Here it comes. The only reason that would happen is the black is back there saying, I am lonely. I'm lonely. Come on back. Alright, we can do this with the green, we can do it with the red, we can do it with the blue. The green and the blue are the ones that you got to at least get to the green before you're going to get any energy. The red just doesn't have enough oomph. But you can see the red much easier than you can see the green or the blue. Now, if you're a real geek and you want to know about the energies and the weights and the whole thing and the masses and how these nucleuses are constructed and how they will grow in size, and hopefully we can figure out how copper is so conductive. Why is it so conductive? And you should see what happens with a big heavy duty weight. Well, I'm going to show you a magnet and a big chunk of copper. It's just amazing. It has a cloud around it of electrons, which are the negative electron particles. Now, iron you can magnetize. Copper you can't really magnetize that. Iron, why does it get magnetic and not magnetic? There's some things I need to understand that I don't understand yet. So there's work to do here. But I think I got a good handle on the nature of all the particles in the universe that exist are made of these two bitty particles, which is the ones that they show at CERN. I'm showing the same thing they're showing, only I have expounded a little more on it. And because we use light, we can actually see these things happening. They're just digging through debris. I'm sorry, that's just the truth. Okay, I believe I showed you that white particle spinning in the reverse. It's supposed to spin to the right, it was spinning to the left. This appears to be that particle, and it has some form to it, strange as it may be. And then this form concussed with this field, and it like skimmed off a bit of it, spinning I don't know which way, but it's concussing. Anytime you see glow, you have concussion. Now, and then it continued on with like a ghost particle. It's not a full Higgs. I don't know. That's the only time I've ever seen it. Here you can obviously see light spins, and it spins. Some spin over that way, and you see them line up over here. Some will spin and come on over this way, and you see them over here. They all want to be away from each other. That's why all of these tiny little patterns show up, because you push, it's like stay away, stay away, stay away, and it just goes down its line, the next one goes down. That's what the interference patterns are pushing and shoving of magnetic particles that are all white, and they don't want to be next to each other. Get away, you get away, you get away, you get away. All right, I'm going to leave you with this because we're starting to look into this. Rod Warren's nephew, Dylan, sent me these pictures of the night sky, and it blew me away. He had a new phone with some new app that shows magnetic field lines. Now, and I can see everything's a dipole. You see, they're all dipoles. There's some strange stuff here, though, that I cannot explain whatsoever. Now, let me show you another one, though, that just tweaks me out. I think it's Venus. All right, this one here, I think, is like a double field. I think this one is spinning backwards, too. Instead of spinning to the right, it's spinning to the left. And this is concussing this way instead of on this side. Now, why do I make this claim? Because of this. You see this here, this field? That's the magnetic field of a spinning particle, whether it's spinning this way or spinning that way. It doesn't matter. It doesn't matter. You're going to get a field like this. However, the normal spin is a right-hand spin. Venus spins left, which means not only is it spinning through the universe in the same way we are, which creates this field here, it's spinning backwards, creating another field. You see this field? That's not right. That's totally not right. I think this is a double-fielded particle, which happens to be Venus because it's spinning backwards. This is not right. That is absolutely not right to have two fields on the same part if it's spinning against the particles that are coming at it. This is spinning with, it's wrong. Let's go with that. You see one more time? You don't see a secondary field coming in here. You got one field. I don't even know where it's going to. But you shouldn't have two fields. It's just not right. Let me show you something else about Venus. You see that? That's Venus. That is just not right. It's because it's going backwards, and the interaction is just crazy. And I'm going to show you another one about Venus where you'll see it's just this is not the correct type of interaction you have if it was spinning with a right-hand spin. Now this, somebody sent me and said, what do you think? This is the sun sending out its energetic particles. This is Venus. You see how it's got a half a black and a half a white field? That's not right. It would having a black inside and a white inside of itself. That's what the crazy thing we just saw a second ago. That's not supposed to be that way. Now, here's Earth. Here's what happened. This particle right here is like it's coming through space, and all of a sudden a field like this, a big field like this, went out and pushed that away or blocked something, and they met here in the middle, I believe, or as I recall. And at first I said, wow, that's got to be some kind of an alien trying to shoot at us, and we're shooting back. But then I started to think, this would have a potential charge racing through all of these charged particles. It would be building up a charge, and if we might have, it might have discharged towards us, and we would meet it in the middle. So that would just be a normal static discharge, and instead of coming all the way and hitting the Earth, we would be sending our own electrostatic field up to meet it in the middle. So it might not be anything other than that. But it was very strange looking. This happened 2021, at December 11, 2021. Now, we're going to get deep into how neutrinos travel. Do they travel faster than other neutrinos? Do they still all go the same speed regardless of the color variety they are? I know the green and the blue are much more powerful than the red, but let's see what Fermilab has to say. Okay, once again, Fermilab, and I tried contacting all these people many times, and I don't seem to get through, but she's asking how fast do neutrinos travel. And they always ask, if you have any questions, contact us, and boy, I've tried. Here goes.
Neutrinos are really speedy. These little particles can travel straight through the entire Earth in a fraction. Pound for pound of all the particles with mass, they are the fastest, almost travelling at the fastest possible speed in the universe, the speed of light. But not quite. So exactly how fast are they? That's tougher to say. Today on Even Bananas, I feel the need to showed that the mass of the neutrino has to be less than 0.8 eV over c squared. Slower. One of the special things we know about neutrinos is that they change flavour as they travel. That is how close to the speed of light they travel. So you can see why. Electron recently showed that the mass of the neutrino has to be less than 0.8 eV over c squared. So let's say Catron is just shy of finding the
All right, I'm not going to drag you through all the details, but they've realized that the neutrinos don't exactly go the speed of light. They're very, very, very close, almost the speed of light. And I know why, because they're being backed up at the Venturi. I say you accelerate them and then you slow them down to just below the speed of light, and then they go through the Venturi. All right, here's my claim, is that we have accelerated it. That sure looks like acceleration to me. That's where the particle was, and it's pushing forward, and then it says, gets sucked forward, but then all of a sudden, these are like little balloon bags, little pillows, and it hits against them, and so it slows down as it comes. And the first thing you're going to see is the tau neutrino, and then you're going to see the regular photon, which consists of everything together, both neutrinos back to back, which is 2 electrons, and then you're going to see them all separate here and then come back together. All right, so I say light can accelerate, and it slows down as it pushes back against itself. That's why a neutrino is almost the speed of light, but just a skosh under.